Okay, here we go. Okay, so something, list please, phones away, all that good stuff. Okay, so I would sort of expect you to maybe, know the important equations, just because it's, we're gonna use them so much. This is probably the one you're least likely to remember, but you should remember it anyway. What is the pendulum equation? The equation that relates period to the length of the pendulum.
Period equals.
Okay, so period, capital T equals 2 pi. Good. Length of the pendulum over the acceleration of gravity. Good. Okay, so then, now there's a couple ways we can do this one. We could find out what the period is that corresponds to a length of 8.7. That's fine to do. Okay, and then if we want to know what length of pendulum would be needed to double the pendulum's period, whatever answer we get for t, we'll just double it and go back to this equation and solve for L, right?
Yeah.
Yeah.
That make sense? Okay, so let's do that then. So if I want to solve for the t that goes with this length, we'll call that TS for the short period is going to be 2 pi times, starting this thing going, it takes a while, times the square root of 8.70 divided by 9.80. And it's going to give us an answer here in a second. Go away. There we go. Oh, good. Okay. Okay.
Did you say it was doing Christmas music?
Definitely
You say it was
not.
playing Christmas music?
No, there's something weird with my headphones. It makes my phone wig out like that.
Oh.
I don't know what's wrong with it.
Okay, so what do we got here? So we get 2 pi. Whoops. Go away. How come that won't undo it? Oh, never mind. Guess we're good. So 2 pi times square root of 8.7 divided by 9.8, right?
Yep.
And we get that, about 5.92-ish, right? And some change. So that's the period associated with 8.7 meter length. So now if we want to find the length associated with double that period, well, now we'll go back to our original equation and, whoops. We will plug in, what's that going to be, 11.84 equals 2 pi times the square root of L over 9.8, right? Does that make sense? And we're going to solve for L, yeah. So to solve for L, what do we do?
Divide by 2 pi.
Divide by 2 pi, good. So we're going to get, first step is going to be 11.84. And really, I'm going to use the number in my calculator, right?
I was gonna ask
Okay.
that.
Divided by 2 pi equals square root of L over G. So now what?
I thought you was
18.
square it.
Oh, you're right. So, yeah, it is 9.8. You're right. Square both sides.
Yep.
Right? So then I get this. Multiply each side by 9.80.
Yep.
And I got it, right? Okay, so what's that give us?
Wait, just,
34.8.
Okay, so that gives me this number
times two.
times 2 divided by the quantity 2 pi is that. Gotta square it. Times 9.8 is 34.8. Well, interesting. 34.8. Does 34.8, is that related to 8.70?
Yeah. Yeah. Times four.
Yeah, it's 4 times bigger. Okay, so
Really, you
could
just-
we have maybe known the answer before we even did this thing?
Mhm.
I would claim yes, because if, look at this now, if g is a constant, right? 2 pi are constants, the only variables in this equation are these two, period and length. Period is proportional to the square root of length, right? Does that make sense? So in order for me to double the period, if I'm gonna increase the left side of this equation by a factor of 2, multiply it by 2, what am I gonna have to do to L to make the right side twice as big? Gonna have to increase it by a factor of 4, aren't I? Because it's being square rooted, and the square root of 4 is only 2. See what I'm saying?
Mhm.
It might be easier to think about it in reverse. If I increase the length by a factor of 4, what's that gonna do? I just wanna show you, just bear with me here on one thing. I know Delaney's she's gonna rebel against this,
Mhm.
but I'm gonna show you one thing here. If I were to increase L, so let's say this is my L naught. It's my original L. I'm gonna say that my L final equals 4 times. Times my original length, right? So we'll make that substitution as my original period. So my T final then is gonna equal 2 pi times the square root of 4 times my original length over G. And just watch what this does here. This to me is a much cooler way of thinking about it. Okay, so now think about this in terms of algebra. Is there a property of radicals that helps me here? If I have the square root of a times b, that's the same thing as saying what? Square root of a times square root of b, right?
Yeah.
Okay, everybody agrees? So I could rewrite this as 2 pi times the square root of 4 times the square root of my original length, L naught, over G, right? Well, what is the square root of 4? 2. So isn't that really just the same thing as saying 2 times 2 pi times the square root of L naught over G?
Yeah.
But what's this whole thing? That's my original period, isn't it? Right? So what I get, I increased my length by a factor of 4, and what I got back was my twice my original period. See how that works?
Mhm.
Okay.
So
And-
if it was triple, you'd do 9.
Exactly. So if it was triple, it'd be 9. Exactly. Right. Okay. And so what I just want you to see here for future reference is that because this is inside the square root and that's outside the square root, any change of a factor of 4 here, because it's square rooted, only brings about an actual outside change of 2. Okay.
But the answer's 34.8.
But the answer's 34.8. Exactly. Yep.
Sure.
No, that's good. That's what we were looking for. Okay, 34.8.
So, would you just be able to say like, in the equation, like 2t equals 4l? Like if you're making an equation?
Well, the way I would have probably done this in college, if I were doing this one, I would have just said because t is proportional to the square root of L. Yeah, I would have said then because of that, it has to be four times as big. If L's doubled, yeah.
So go to the next problem.
Okay, next problem. All right.
We should do the grocery one, because that's like 3 on the review.
Okay. Grocery one?
With the balloons. Yeah, the balloons. Just do them all. Maybe do the trumpet. Oh no, number 6.
The grocery ones, balloons, and maybe there's some
Like, you know, like the
Can we do that? Like,
trumpet and the balloons.
oh yeah?
Hmm?
Could we do like the dragster one? Or like one sandwich in that one?
Sure.
Yeah, the dragster one too. No, number 6.
Oh, there's
Yeah, that
okay.
one.
There's the grocery sack one. Let me see which one the dragster one is.
Screw you.
That's not it.
Well, whatever's worth 3 points, change that one. Obviously, that's important.
Well, what did I do with?
Do that one. That one looks hard.
So I forgot to tape that last one. Sorry.
That's okay. We're all here. We wrote that.
How about we go over to one of the 3 answers?
The 3 answers. Okay, that'll be next one. We'll do one with the 3 answers. Okay. Yeah, that would be a really good one because I know that'd be a good one. Yep. For many reasons. Okay.
There's a typo
Is there a typo in this one?
along a straight icy road instead of.
Oh yeah. You're gonna find a few of those probably. Okay, so what do we got going here? Talk to me about this. We got we know the mass of the car. It's driving at a constant speed along this icy road, and then it slams on the brakes. Your wheels lock. Now, why is that important?
Because you're
Because then you
sliding.
can't hit this
Okay, you're sliding. So, what kind of friction are we talking about?
Hit the dynamic-
Kinetic friction. Good. Okay. We know, and we're trying to find the coefficient of kinetic friction, right?
Mhm.
Okay.
Is that like mu?
Yep.
Okay.
Mu sub k. And so they're k for kinetic, and they're telling us how far it slides, right? So really, what have we got going on here in terms of what's the only force acting on the car? Horizontally, it's friction once we slam on the brakes, right? So we know that the friction force is equal to the whole net force, isn't it? Right? If I drew a free body diagram, there's only one force acting, and it's friction. I mean, vertically there are some forces acting, but we don't really care about those, do we? We just want to know what are the forces acting horizontally to slow us down, right? I guess we could add the vertical ones too, though. Why not? So what are our vertical forces? Okay, we got the weight down and normal force up. Good. So friction is equal to ma, isn't it? Okay. If we knew, and what is the definition of our frictional force? What's our frictional force equation?
Mu. Yeah.
Good. Okay, so friction equals mu sub k times normal force, but maybe it is good that we drew these vertical ones on there because we are going to need them. What's the net vertical force?
0.
0, right? It's only moving horizontally, right? It's not moving. So normal force is equal to what? In magnitude.
Mass times gravity.
The weight. Good. We know vertically that normal force plus or minus mg is 0, right? These are equal. They offset each other. So we could write this then as the frictional force is equal to mu sub k times mg, and that's all equal to ma, right? So there's the equation we come up with, isn't it?
I'm sorry, where did you get the mg from?
Because normal force is equal to mg here.
But it,
right?
Okay, gotcha.
Okay.
Gotcha.
The road's pushing up on the car just as hard as the car's pushing down on the road, okay? Make sense?
How do we know when this like means?
Okay, well, that's what we're trying to find. So, right, so can we solve for that? Do we know everything else? Well, we either know it or can calculate it, don't we? The mass ends up actually being irrelevant, doesn't it?
Yeah.
I gave you mass, but does it even matter? No, I can divide the mass away from both sides of that equation, right? So the frictional force, mu times mg equals ma, but the m's are gone. And doesn't that make sense? It really shouldn't make any difference, should it, how heavy the car is here? The car is just gonna slide the same distance no matter what, right? Okay? So if I solve for mu, all I have to do is divide both sides by g, right? So mu sub k equals a divided by g. Got that?
So you need to solve for A.
Yep, so we have to solve for a. And that's a kinematics
G
problem.
is gravity.
G is gravity,
Okay.
yeah. Okay? Yes?
This is kind of I'm just not understanding it, I guess. So like if the normal force minus the weight equals 0 in this equation,
Mhm.
and doesn't normal force minus weight also equal mass times acceleration?
No. No, it doesn't. Here, you know what, I think we need to do something here. Let me take this, let's look at this free body diagram in more detail. So if the car is driving in this direction and slowing down, so here are the forces acting, right? We've got a frictional force acting down to the left, and then we've got our normal force pushing up and gravity pushing down, right? Okay, so let's look at this in terms of the vertical stuff and the horizontal stuff, right? So what about the vertical stuff? So that we're looking only vertical, so the net force just the vertical net force. Well, what is it? Positive is up,
0.
negative is down, right? So I get normal force minus mg, and it equals 0 because the car is not accelerating up or down, right? It's just moving horizontally across the ice, right?
Yeah.
Okay, so that tells us then that the normal force equals mg. We could also just see that from the free body diagram, and that's how we've usually even done it, right? We've just said, okay, on the free body diagram, if these are the same magnitude, one point's up and one point's down, it's not accelerating vertically, then we can see that these two things have to be pushing with the same magnitude against each other, right? Does that make sense? Okay. So there's one thing we know. Now, what about vertically? Well, vertically, there's only one force, right? There's only one force acting vertically. We know that, horizontally, sorry. The net force horizontally, there's only one thing acting, and that's friction. Well, friction is equal to mu times normal force, but we know that normal force is the same thing as mg. Why is that important to us? Well, because what's normal force? We're not given anything in this problem about normal force, right? But we are given the mass of the car, not that we end up needing it, but we're given the mass of the car, and we know g, right? We live on Earth. On Earth, g is 9.8. So this doesn't mean a lot to us, but that does, right? So we want to replace the normal force with something that we know, which is mg, right? So then we get the frictional force equals mu times, we'll replace the normal force with an mg, and we know from Newton's second law that net force equals ma. Well, there's only one force acting, so that is the net force, and so it's equal to ma. And so that's the equation we have to work with. Okay?
Didn't we just figure that out earlier?
We did, but I just wanted to put it in the context of maybe, the question was asked about, how did we know this, I think, is kind of what Riley was asking.
I had an equation written down on my paper, I must have, so that was it.
Okay. Okay, so, yeah, so we're back to here. So we know that mu times weight, so the frictional force equals, that's the only force acting, so that's our net force MA. We can divide the mass away from both sides, which is always great. That means it's independent of mass, doesn't matter. So now we can just divide both sides by g to solve for mu. And we get the answer, mu just equals A over g. Just have to find A.
So,
Yeah, so let's find A. So if we go back up to our problem here, what's the kinematic stuff that we're given? Well, the initial velocity, 18.8, right? Before it hits the brakes.
You don't have time.
Seriously?
just,
We'll just do as much as.
You need a question, you don't.
Oh, okay, I got you. Okay. Final velocity? Thank you. You may be right, though.
That's your gut.
Okay, so final velocity is 0 because it's coming to rest. We know the displacement is 134, right? Takes 134 meters to stop.
so v squared minus v dot squared equals ATV, no,
And then we're trying to find A, right?
oh yeah, thinking.
Okay, so then we're going to use the non-t equation. V squared minus v naught squared equals 2a delta d, right? Okay, we know that v is 0, so that one goes away. Right, and now we'll just solve for a. Divide both sides by 2 delta d. So a equals minus v naught squared over 2 delta d, and we can plug that into our calculator. We know that stuff. So that's negative, what was v, 18.8? 0.8 squared divided by the quantity 2 times 134,
Yes.
so 268. Gives us negative 1.31 blah blah blah. So all I have to do is divide that by g, right? Okay? Divided by 9.8 gives us.
Would we actually say it was negative?
Oh, no, whoops. No, we don't.
Wait, what's not negative?
We don't, we just want the magnitude. It's not we don't treat it as being negative, right? Coefficients can't be negative. So it's roughly equal to 0.135 to 3 places. No, there are none. Nope, look, it's acceleration over acceleration, which makes sense because coefficients are not, they're unitless.
You said there's no units?
No units, yeah, it's just a number.